Hi everyone, back to a new awesome video, and today we're going to continue with our series about classical mechanics. We have already finished up with collisions and we're going to enter the world of rotations. And that will keep us with lots of videos till the end of this classical mechanics series. Today, we will start with the notion of rigid bodies, because that's what we are going to work with. Not point masses, point particles, as we have been working through the whole classical mechanics series, but bodies with an extended mass and that they can rotate and move, translate, etc. After that, we're going to announce Chasles Theorem, a very important theorem in movement and translation and rotation of rigid bodies that help us simplify greatly all of our calculations. And after that, we will start introducing the notions of angular velocity and acceleration. So let's start. Great, let's start introducing this notion of a rigid body. Imagine this is our rigid body. For it to be considered so, it has to comply one condition. Imagine we have over here a particle J of our rigid body, and over here we have a particle K of our rigid body. We could draw a vector joining them, which would be R, J, K, and this vector has to fulfill the following condition, and that is that the modulus of this vector rjk is constant. So no matter what happens to this body, you throw it, you move it from here to China, you throw it into space, you put it in a vacuum, it doesn't matter. The condition for it to be a rigid body is that these 2 points, and any point in general, so this is for all j and for all k, must stay at the same distance. That is, that the body cannot be deformed, compressed, stretched in any way. And that will help us with our calculations. In reality, most things aren't actually rigid bodies. We have some bodies that can't even be approximated as so, but most of the times there can be some compressions and stretching, but it is so little that we can make the rigid body approximation, which will help us greatly. One example of these rigid body simplifications is announced by Chasles Theorem. It says the following thing. It says that any movement of a rigid body can be divided into 2 components: a rotational motion, in which we are going to have our rotational variables that are going to be pretty equivalent to the ones we have in translation in normal kinematics, and a translational motion. And specifically, I would like to make a small adjustment here, and this is that is a translational motion. So the thing that is going to be moving is the center of mass, and then the body is going to be rotating. That's why usually in kinematics, when we are talking about a block moving or something like that, we just consider the motion of this center of mass along a trajectory, and we don't take into account all the rotation that might take the body. And we can do that because we make use of the rigid body approximation, and we make use, without knowing it, of the Chasles Theorem. Doing this will help us greatly in simplifying the exercises, because we don't have to take into account the fact that each particle is moving but also translating. We can analyze the rotational motion in the center of mass frame, and then we can add to that the translational motion of the center of mass, and that is going to make things much more easy. Now it's time to start introducing some of these circular variables, as I like to call them. But they are really rotational variables and magnitudes we will have to take into account. We will start with angular velocity and angular acceleration. This is going to be pretty analogous to what we did in episode 2 of this series long time ago. So we have our rigid body over here. This is going to be its center of mass. We'll assume it's almost a perfect circular body. And we're going to have our axis over there. That is going to be the x-axis. So we'll go I hat and j hat. And we're also going to consider a random point P just to take into account how things are moving over here. So right around this line, we're going to have our point P right in there. And we're also going to draw the r hat and theta hat, the polar coordinates, right around there. Great. Now we need to have some reference frame in which we're going to measure the position of our point P, and we're going to use polar coordinates. Therefore, we're going to be interested in this angle theta, which is, if the body is rotating, is going to be a function of time. Now, angular acceleration and angular velocity are going to depend on this angle theta. Specifically, we'll also draw our k hat vector over here. The angular velocity represented by a w, it's going to be equal to d theta dt. It's going to be rotational motion in this direction, velocity and angular velocity in that direction, how the angle changes in time. And we are also going to give it a direction because it's a vector, as you can see, and the vector is going to be k hat, and I'll explain why. So if the particle is rotating in this direction, you need to follow the right hand rule, and with your right hand roll it over through where it's going, the particle, follow its movement, and then your thumb is going to go sticking out into the air. In that case, we'll have this k hat positive, or it can be pointing into the chalkboard, which in that way would be expressed by a cross, and it's going to be a negative k hat direction. So if it was rolling this way, it would be a negative k hat direction and a negative angular velocity. Now, similarly, if we carry a similar analysis, we can reach the conclusion that alpha, which is our angular acceleration, also function of time, is going to be once again the derivative, this time of the angular velocity, and we can take that vector out of the equation, and you see it also follows this k hat and minus k hat convention when rotating. Almost all circular variables are going to behave this way if they are vectors. Also torque, as we'll explore in later videos, and different other magnitudes are going to follow the exact same k hat convention. Now we would like to express this alpha in terms of the position of theta, and we can do so very easily, similar to what we did in that first video or second video of this series. If we take w and we're going to integrate this, the theta, let me erase vectors, and we're just going to have some integrals from t equals 0 to t equals t, some primes over here, and the same over here from zeta equals zeta 0, our initial angle, and theta as our upper limit. Now, when we're integrating this, we find that w, for now, we're just going to take it as a constant, as if it's not a function of acceleration, and by integrating it, we're going to find that it's w times t is going to be equal to theta as a function of time minus our initial theta sub 0. Therefore, theta of t is going to be equal to theta of 0 plus wt, in the case in which w is constant. However, most of the times we're also going to have some alpha acceleration, and we can carry a similar process to find that w of t equals w0 plus alpha t. Now we can integrate once again this quantity as if we had it over here, and we will find the final formula. Theta of t equals the initial angle we had plus the initial velocity we had times time plus 1/2 alpha t squared. And this equation should be pretty familiar because it's the exact same equation we had for kinematics, but for the circular rotation variables. That is all for today. I hope you're excited about this new circular motion stage of our classical mechanics series, and that you also got a sense about how we're going to use these different tools to our advantage when mixing rotational and translational motion. Furthermore, I hope you also start seeing the parallelism that we can find between our translational variables and the rotational variables, such as this kinematic equation, which is the exact same but with different variables. Any doubts left, you may ask them in the comment section and I'll try to answer them in the best way I can. Remember to like the video if it was the case, press the subscribe button, the bell, and follow us on social media so that you don't miss any of the new videos. See you another day with more Physicawesome!